Hello everyone, welcome to our AI development series. In our last tutorial, we explored the basic of LangGraph and built a chatbot. Today, we are taking it up a notch. We will be diving into Tavily Search and introducing memory capabilities in LangGraph. So get ready to supercharge your AI agent with up-to-date information and improve context retention. Let's get started. In this tutorial, we will combine the power of LangGraph with Tavily Search to create an AI agent that can access and process the latest information from the web. We will also explore how to implement memory in LangGraph, allowing our AI agents to maintain context across interactions. Whether you are building a research assistant, a fact-checking bot, or any AI application that needs current data, this tutorial will equip you with the right tool to make that happen. Tavily Search is not your average search engine. It's specifically designed and optimized for large language models like the one we use in our AI agent. What sets Tavily Search apart is its ability to provide factual, efficient, and contextually search results tailored for AI consumption. Unlike traditional search engines, Tavily supports complex workflows, allowing for iterative improvement and even human-in-the-loop features. This makes it an ideal partner for our LangGraph-based agents, enabling them to access and process up-to-date information in a way that is tailored for AI consumption, understanding, and decision-making. To start using the Tavily API, you will need an API key. There are both free and paid plans, but the free one is enough for testing and experimenting. To use Tavily Search in our project, we will need to generate an API key. Here's how to do it. Go to the Tavily AI website and create a free account using your email, or you can sign in with Gmail. Once you log in, you will be directed to the page where you can generate an API key. Click on Generate a new API key, type the key name, click Create. Copy your new API key and keep it secure. We will use this in our code to authenticate our request to Tavily. After that, you need to add the Tavily API key to the .env file. And here is my Tavily API key stored in the .env file in the same directory as the Jupyter notebook of this tutorial. Memory in LangGraph is a game changer for creating more intelligent and context-aware AI agent. It allows our AI agent to retain information across multiple interactions or steps in a process. This is very crucial to maintain coherent conversation, handling complex tasks, and provide personalized responses based on the past interaction. In LangGraph, we can create different types of memories, such as short-term memory for immediate context, or long-term memory for returning important information over extended period. By incorporating memory, our AI agent can learn from past interaction, adapt their responses, and provide a human-like experience. Before we start, I highly recommend you watch my previous tutorial titled Introduction to LangGraph to get a solid foundation for what we are about to cover. Now let's dive into our code. We begin by installing the Tavily Python library. This library allows us to interact with Tavily Search API. Next, we import and use the .env library to load our environment variables. This is a crucial step for securely managing our API keys. We then import the Tavily client from the Tavily module and initialize it with our API key, which we have stored as an environment variable for security. Now comes the exciting part. We perform our first search using Tavily. We are asking a simple question. What is the Bitcoin price today? Let's run the code cell now. Let's break down the response we get. The query field confirms the question we asked. The follow-up question and answer fields are empty in this case, but they can be useful for more complex queries. The image array is also empty as our query did not require any image results. The meat of our response is in the result array. Each result includes a title, a URL, some content, a relevant source, and a raw content field which is null in this case. Looking at the top result, we can see that according to CoinDesk, the price of Bitcoins was around $60,000. However, it's important to note that cryptocurrency prices are highly volatile and can change rapidly. The results are sorted by the relevant score, with the highest scoring result appearing first. This helps ensure we are getting the most pertinent information for our query. Finally, we can see that this search took about 2.8 seconds to complete. This simple example demonstrates the power of Tavily for AI-optimized searches. Now let's take a closer look at how we can process and display our search results. We are using a for loop to iterate through each result in the result list of our response. For each result, we are extracting two key pieces of information, the title and the URL. The title gives us a brief description of the web page, while the URL provides the web address where we can find this information. And we are using an f-string to format our output. This allows us to embed the title and URL directly in our print statement, making the code more readable and efficient. As we run this code, we will see each search result displayed on a new line, with its title and URL clearly labeled. This format makes it easy for us to quickly scan through the result and find the information we are looking for. Now let's explore a more advanced search query using Tavily API. We are calling the search method on our client object and passing several parameters to customize our search. First, we specify our query. What are the best programming languages to learn this year? This is a question we want to answer. We set the search depth to advanced. This tells the API to perform a more thorough search, which may take slightly longer but will provide more comprehensive results. We are limiting our results to 7 with the max result parameter. This helps us focus on the most relevant information without being overwhelmed. By setting include images to true, we are asking the API to include relevant images in our results. This can be useful for visual learners or if we are creating a visually rich report. We have also set include answer to true. This prompts the API to generate a concise answer to our query based on the search result. Finally, we have set include raw content to false. This means we won't receive the full HTML content of each result, which can help keep our response size manageable. Now let's print the response. And we get the response. Let's take a moment to analyze the response we have received from our Tavily API search query about the best programming languages to learn this year. This analysis will help us understand how to interrupt and utilize the rich data provided by the API. First, we can see that the API has returned a structured response with several key components. First, query. The API correctly captured our original question. Second, answer. The API provided a concise summary answer, highlighting Python and Swift as top choices, along with mentioning a top 10 programming languages list for 2024. This gives us a quick overview of the result. Third, images. The API returned 5 relevant image URLs, which could be useful if we were creating a visual report or presentation on this topic. Fourth, result. We received 7 detailed search results, each with a title, URL, code snippet, and relevant score. And finally, the response time. The API took 4.25 seconds to process our query, which is reasonably fast for such a comprehensive search. The search results provide a good mix of current information, with many sources specifically mentioning 2024 in their title or content. This ensures we are getting up-to-date information for our query. Now let's look at how we can use Tavily question answering feature. This is particularly useful when we need a quick direct answer to a specific question. We are using the Q&A_search method of our client object. This method is designed to provide a concise, factual answer to our query. Our query here is, who won the UEFA Champions League in 2024? This is a straightforward question that should have a clear, factual answer. We store the result in the answer variable and then print it out. The API will search for the most up-to-date and reliable information to answer our question. When we run this code, we get the answer: Real Madrid won Champions League in 2024. This demonstrates how quickly and easily we can retrieve specific current information using the Tavily API question answering feature. This capability is particularly valuable when building AI agents that need to provide accurate, up-to-date responses to user queries. Now we are going to take our AI search agent to the next level by combining the power of Tavily Search capabilities with language models using LangChain and OpenAI. This integration will allow us to process and analyze our search results in a more sophisticated way. First, let's import the necessary libraries. The convert OpenAI messages function will help us convert our prompt to a format that LangChain can understand, while chat OpenAI will allow us to interact with OpenAI language model. Next, we define our query. This query is more specific and technical, demonstrating how we can use our AI search agent for complex topics. Now, let's perform our Tavily search. We are using client.search method, limiting our result to 5 and setting the search depth to advanced for more comprehensive results. We are only keeping the result part of the response. Next, we set up our prompt for the language model. This prompt is crucial. It consists of two parts: a system message that defines the AI roles as critical thinker and research assistant. Second, a user message that includes our Tavily search result and instruction for how to use this information. Now we need to convert this prompt to a format that LangChain can understand. So we create a variable lc, which is LangChain_messages, equal to convert OpenAI messages, and we are converting the prompt. Let's run the code cell now, and we get our response in a format that LangChain can understand. Finally, we are ready to invoke the language model. Here we are using chat OpenAI class to interact with the GPT-4o mini model. We invoke it with our converted message and print the content of the response. Let's run the code cell now, and we get the response. Here we get a detailed report on flow engineering in agentic applications and LangGraph, based on the information from our Tavily search result and processed by the GPT-4o mini model. This combination of Tavily search capabilities with OpenAI language model orchestrated through LangChain demonstrates the power and flexibility of our AI search agent. It can not only find relevant information, but also analyze and clean it into a coherent, detailed report. Again, I recommend for you to watch my previous tutorial about Introduction to LangGraph. This will give you a solid foundation for understanding the concept we are about to dive into. Now let's build our LangGraph AI search agent using Tavily Search. We will go through this code step by step. First, we will import the necessary component and set up our memory. This memory saver will help our agent maintain context across interactions. Next, we import various types and tools we will need. We define our state type, which will hold the messages in our conversation. Now let's set up our graph and tools. We are using the Tavily Search tool, limiting result to 2 for simplicity. Then we set up our language model. We are using the GPT-4o mini model and building our tools to use it. Next, we defined our chatbot function. This function will process the current state and generate a response. Then we add nodes to our graph for chatbot and tools. After that, we set up the edges in our graph. This defines the flow of our agent. It starts with the chatbot, can use tools when needed, and always return to the chatbot after using a tool. Finally, we compile our graph. Let's run the code cell. Now that we have built our LangGraph, it would be helpful to visualize its structure. This can give us a better understanding of how our AI search agent processes information and makes decisions. Let's look at the code that attempts to display our graph. First, we import the necessary functions from IPython. Next, we use a try except block. Inside the try block, we are doing several things. Graph.getGraph retrieves the underlying graph structure, and draw_mermaid_png attempt to draw the graph as PNG image using the mermaid library. This PNG is then wrapped in an image object. Finally, display is called to show the image. Let's run the code cell now. And we get the visual representation of our LangGraph AI search agent. This diagram illustrates the flow and decision-making process of our agent. Starting from the top, we see the start node. This is the entry point of our graph, representing the beginning of any interaction with our agent. Moving down, we come to the chatbot node. This is the core of our agent, where user input are processed and responses are generated. The chatbot node is central to our graph, showing that it is the primary point of interaction. From the chatbot, we see two possible paths. A dotted line leading to the end node on the right. This represents the possibilities of the conversation ending after the chatbot's response, perhaps if the user query is fully answered or if they choose to end the interaction. A solid line leading down to the tool node on the left. This path is taken when the chatbot determines it needs additional information to answer the user query. The tool node represents our Tavily Search functionality, which the agent can use to gather more information. It's very important to note that we see a solid line leading back from the tool node to the chatbot node. This illustrates that after using a tool, the agent always returns to the chatbot to process the new information and formulate a response. This cyclical structure between chatbot and tools allows our agent to gather information and refine its responses as needed. The agent can make multiple passes through this loop in a single conversation, ensuring it has all the necessary information to provide a comprehensive answer. Now let's set up a loop for user interaction. Let's break down what's happening here. We set up a config dictionary with a thread ID. This thread ID is used internally by LangGraph to maintain the conversation context. In the graph.stream method, we pass this config as a second argument. This is crucial for maintaining memory across interactions. We don't need to explicitly save or update any memory. LangGraph handles this internally based on the thread ID we provide. The context is maintained automatically across multiple calls to graph.stream with the same config. This approach allows our AI search agent to remember previous interactions and maintain context throughout the conversation, all without explicitly memory management on our part. Let's run the code cell now. What are the major news in technology this week? And we get the answer. Now let's ask it to summarize it. Can you please summarize it? And we get the summary. The AI search agent is indeed working as intended. Let's break down what we are seeing in this interaction. In the initial query, the user asks about major news in technology for the week. The agent used the Tavily Search to gather recent information. We can see this from the raw search results included in the response, which contains URL and snippet from the technology news sources. The agent then processed these search results and compiled a list of 8 major technology news items, covering a range of topics from AI and robotic to medical technology and energy. When we asked for a summary, the agent understood this was referring to the previous response. It did not perform a new search but instead summarized the information it had already provided. The agent effectively condensed the previous 8 detailed points into a concise summary, maintaining the key information while reducing the overall strands. The summary accurately reflected the detail from the original response, showing that the agent maintained context between interactions. This interaction demonstrates several key capabilities of our AI search agent: ability to perform relevant web search using Tavily, skill in cleaning information from multiple sources, context awareness across multiple interactions, capacity to summarize information on request, adaptability to different types of queries. The agent performance here showcases the power of combining a large language model with real-time web search capability and maintaining conversation context. It's able to provide up-to-date information and then work with that information in subsequent interactions, just as a human research assistant might. This example illustrates why this type of AI search agent using LangGraph can be so helpful for tasks requiring current information and the ability to process and summarize that information in various ways. And there you have it. We have built an AI agent that can access up-to-date information using Tavily Search, and it can maintain context using LangGraph memory capabilities. This opens up a whole world of possibilities for creating more intelligent, informed, and context-aware AI applications. Remember, this is just the beginning. You can build on this foundation to create specialized agents for various tasks, from AI research assistant to fact checker and beyond. I encourage you to experiment with different types of memories and explore other features of Tavily Search and push the boundaries of what your AI agent can do. Thanks for joining me on this tutorial. If you find it helpful, don't forget to hit the like button, subscribe to my channel, and ring the notification bell for more AI development content. Until next time, happy coding!